Every single year, more than 1 billion brand new tires hit the roads around the world, and just as many reach the end of their journey, piling up in landfills and tire cemeteries. In the US alone, over 250 million tires are recycled annually, saving the planet from mountains of waste. But have you ever wondered what really happens to those black rings of rubber that carried cars across thousands of miles? They don't simply vanish. They're torn apart, melted down, and ground up, only to be reborn into something far more extraordinary. And here's the twist: you probably walk on their second life every single day without even realizing it. Stick with me until the end, because I'll reveal a secret that will forever change the way you look at an ordinary tire. Our journey begins in a tire graveyard, acres of land covered in mountains of discarded rubber. These tires may look abandoned, but their story is far from over. This is where the brutal yet ingenious process of recycling begins. A massive industrial shredder, imagine a steel Tyrannosaurus, devours entire tires with terrifying force. Its enormous rotating shafts, armed with steel hooks, rip the tires into palm-sized chunks. As this chaos unfolds, something important is released: steel cords. Every tire hides a skeleton of steel wires, and as the shredder tears rubber apart, these cords break free like shiny metallic webs. But rubber and steel must part ways. Enter the giant magnet. Suspended above the conveyor, it pulls steel cords away from the shredded mix with a deafening screech. The separated steel is sent for remelting, while the rubber continues onward. Still too coarse, the pieces enter a granulator, a coffee grinder the size of a car. Here, sharp blades grind them down to fingernail-sized granules. During this step, another hidden ingredient emerges: textile fibers. Nylon and polyester strands, once added for tire strength, are blown away with streams of powerful air, leaving only clean, heavy granules behind. The rubber isn't done yet. It passes through cracker mills, where enormous steel rollers crush and grind it down further, producing fine, uniform particles, known as rubber crumb. This crumb looks like black sand or caviar, each grain only a few millimeters wide. Packed into 1-ton bags, this material is now ready for its rebirth, and its destination might surprise you. At a stadium construction site, workers roll out vast carpets of artificial turf, but the grass blades lie limp and lifeless until the secret ingredient arrives. A machine spreads layers of quartz sand to stabilize the turf, followed by a blanket of black rubber crumb. These billions of tiny particles fill the space between blades, holding them upright and creating a cushioned layer beneath athletes' feet. The result: every sprint, jump, and fall is absorbed by microscopic trampolines, protecting joints and preventing injuries. A final combing process fluffs the field to perfection, leaving a green expanse ready for play. What looks like ordinary grass is actually a hidden monument to recycling, made possible by mountains of old tires. Here's the staggering part: building one football or soccer field requires 20,000 to 40,000 tires. Across the US, over 13,000 artificial turf fields now exist, meaning more than 260 million tires have already found new life beneath athletes' feet. That's nearly an entire year's supply of discarded tires, transformed into something useful, and the benefits go beyond waste reduction. Artificial turf fields save up to 1 million gallons of water per year compared to natural grass, while eliminating the need for fertilizers, pesticides, and constant mowing. But recycling doesn't stop with tires. In another corner of industry, a material stronger than steel and immune to rust is quietly revolutionizing construction: fiberglass rebar. Every year, billions are spent repairing rust-damaged infrastructure, like bridges and parking garages. Steel corrodes, but fiberglass doesn't even acknowledge rust's existence. It's twice as strong as steel, 4 times lighter, and increasingly in demand. The process begins with thousands of glass filaments, thinner than human hair, stretched from massive bobbins into one thick bundle. This bundle is immersed in sticky polymer resin, polyester, vinyl, or epoxy, infused with hardeners and additives. Then it's drawn through a heated steel die, compressed and shaped into a perfect rod. While still soft, resin-soaked threads are wound spirally around the rod, creating the ribbed texture that grips concrete. Sometimes quartz sand is added for even more bite. Next, the rods enter a curing tunnel, essentially a high-temperature furnace. Inside, the resin hardens into an unbreakable composite, binding millions of glass fibers into one indestructible structure. At the end of the line, Pulling devices clamp and drag the rods forward at a steady pace until they reach the cutting saw, where they're trimmed into 20 or 40-foot sections. Still warm, they're bundled and sent off to replace rust-prone steel in construction projects worldwide. What makes fiberglass rebar revolutionary? Weight, strength, and durability. Being 4 times lighter than steel slashes transport costs, workers can carry bundles by hand, no cranes required. Despite being lighter, it's twice as strong in tension, allowing for thinner reinforcements without sacrificing performance. And its biggest advantage, it doesn't rust. While steel-reinforced concrete may last 50 years before corrosion takes its toll, fiberglass structures can last over a century with minimal maintenance. This material is already shaking up the global market, which grows 10–12% every year. Engineers are now looking at traditional steel and saying we can do better. The future of construction may very well belong to composites like fiberglass. Every year, more than 9 million tons of copper scrap are recycled worldwide. That's enough to build 1,800 statues of liberty. But here's the question: where do those old cables, transformers, and wires actually go? And how do factories, where temperatures soar past 2,000 degrees Fahrenheit, transform discarded scrap into the lifeblood of modern civilization? Stay with this story until the end, because you'll discover a secret about copper recycling that almost no one knows. The journey begins in the vast warehouses of recycling plants. Piles of copper scrap arrive, industrial power cables, as thick as your arm lying side by side with fragile household wires, chunks of old transformers stacked next to the remains of construction wiring. Each piece has lived a different life, but now they all share one purpose: rebirth. The process starts with sorting. Skilled workers carefully separate scrap by type and contamination level. Pure copper wire is pulled away from insulated cables. Thick industrial wiring is kept apart from delicate home appliances. This step may look simple, but it's absolutely critical. Every type of copper demands a different approach. Skip this step, and the entire process collapses. Next comes mechanical cleaning. Massive shredders slice cables into fragments just a few inches long. Then, using the difference in density between copper and plastic, separators do their work. Vibrating tables and air currents strip away insulation and rubber, leaving behind relatively clean copper pieces. But the real transformation hasn't even begun. Inside the furnace hall, the atmosphere changes. Huge induction furnaces roar as they heat copper beyond its melting point of 1,984 degrees Fahrenheit. Solid fragments turn into glowing, liquid fire. Cold, lifeless metal becomes a golden red molten river. Here the impurities reveal themselves. Some float to the surface as slag, others dissolve. Metallurgists add fluxes, special agents that bind to unwanted elements, making it possible to skim them away. This is the first purification. But to achieve perfection, copper must endure electrolytic purification. The molten metal is poured into baths, where thousands of volts of electric current course through it. Impurities like iron, zinc, nickel, and lead are drawn to electrodes, leaving the copper cleaner with each passing hour. Every half hour, chemists test samples, ensuring the composition approaches near total purity. When the copper finally hits 99.9%, it's ready for the next step. The molten copper is cast into molds. Ingot molds preheated to nearly 1,800 degrees Fahrenheit prevent shock cooling. The copper solidifies slowly, forming flawless ingots weighing up to 100 pounds or cylindrical billets that will soon be drawn into wire. The billets enter the wire drawing machines, which stretch them thinner and thinner. A billet first passes through a 3-inch die, then a 2-inch die, then even smaller. Each pass makes it longer and thinner, transforming a heavy cylinder into a flexible wire. The force behind this transformation is immense. Motors with 500 horsepower pull the copper with tens of tons of pressure, but copper's natural plasticity prevents it from breaking. Laser devices measure diameters with microscopic accuracy. If the wire shows even the smallest scratch, the process halts. The stakes are high. This copper wire will soon carry electricity powering cities. After final quality checks, measuring resistance, conductivity, and strength, the wires are insulated. Depending on their purpose, they might be coated with PVC, polyethylene, or advanced materials, then twisted into power, communication, or specialty cables. Spools 3 or 4 feet wide are carefully wound and labeled, certified by Underwriters Laboratories to meet strict American standards. What began as discarded scrap now becomes the foundation of modern life, ready to serve for decades. But copper recycling is more than technology. Basalt and slag melt and transform into golden threads, spun into fibers thinner than human hair. The result? A fluffy, fireproof, sound-absorbing material that keeps homes warm, quiet, and safe. An industrial cotton candy spun from stone, and the chain of industrial transformation doesn't stop there. Consider particle board, the backbone of modern furniture and construction. Over 108 million cubic meters are produced globally each year, recycling 16 million tons of wood waste. What was once discarded, shavings, sawdust, and even old furniture, now becomes sleek, durable boards. Through a process of chipping, drying, resin bonding, and hot pressing, the waste is pressed into 3-layer sandwiches with smooth outer layers and a strong inner core. It's a material born from trash, reshaped into tables, shelves, and cabinets, a recycling revolution that saves forests and fuels sustainable design. From ore to steel, from slag to insulation, from wood waste to furniture, one truth emerges. Industry has mastered the art of transformation. Nothing is wasted, and everything can be reborn. Behind the fire, the roar and the blinding glow lies a story of human ingenuity, a relentless drive to shape the raw chaos of nature into the ordered skeleton of civilization. Each spark, each molten river, and each board or roll of insulation is not just material, it's a piece of the modern world, forged in fire, reborn through innovation, and destined to build the future. Inside the massive press, the wood chip mass is subjected to 2 unstoppable forces. First, enormous pressure, tens of kilograms per square centimeter, compresses the chips so tightly that not a single void remains between the particles. At the same time, the heated plates of the press, scorching at nearly 400 degrees Fahrenheit, transfer their heat deep into the mat. That heat sparks a chemical miracle. The resin begins an irreversible polymerization process. What was once a liquid glue instantly transforms into a rock-hard polymer, binding millions of wood particles into a single unified structure. Within minutes, a loose mat becomes a hot, solid, and completely monolithic particle board. But this transformation doesn't end here.